Yeah, you can start.
Hello, everyone. I hope you're enjoying the symposium. I'm actually very upset for not being there. It really hurts my heart. But knowing that you're having great time helps. So here and now I'm here to introduce Ceyhun Elmacıoğlu. We worked on Kirby calculus and read a recent paper together. Ceyhun is an undergrad and about to finish his undergrad in Lafayette College and will be applying for graduate student schools next year. But I think he's already a great topologist. So, and you'll see now. Okay, Ceyhun, you can start now.
Hopefully everyone can hear me right now. So today I'll talk about types of obstructions from genus bounds and definite form manifold. I know that it probably sounds a bit complex. I'll try to explain every part of it. So let's have a plan. So first we'll talk about the knot theory background, then some form manifolds, because the main proof that we want to have at the end uses form manifolds, and then thirdly, we will also talk about something called the minimum-genus function of a form manifold, which is going to be the main tool that we need for this proof. So to start with the basics, assuming everyone knows that Sn is the n-dimensional sphere, Bn is the n-dimensional ball, and we will only need CP2. CP2 is the space of complex lines through origin in C3. It's the projective space, the complex projective space. And also when we're dealing with knots, we have the knot diagrams, and in the knot diagrams, we either have a positive crossing or a negative crossing. The crossing on the left is negative, the one on the in the middle is a positive crossing. You can find it with the right-hand rule. And when we have, let's say, two negative crossings, then we say that it's a full negative twist. So sometimes we call a negative twist, a negative crossing also a negative half twist. Again, the basics, we can see a knot as an embedding of an S1, which is a circle, in S3, where we see S3 as R3 union a point. And some examples would be the one on the left is the famous figure 8 knot, because it looks like the figure 8, and the one on the right is the unknot, which is the only knot that's not knotted. So when we start dealing with knots, there are different families of knots. In this talk, we will talk about two basic families of knots. The first one is are the slice knots. So a knot is called slice if it bounds the disk in B4. The way to think about this is if you consider S3 as the boundary of B4, then we want, so if you think about S3 that way, then the unknot is the only knot that bounds a disk in S3, and we kind of relax that condition to look at knots which bound the disk in B4 instead of S3. And the second class of knots are what are called the ribbon knots. They intersect themselves, so they bound the disk which intersect itself at ribbon intersections, the arc intersections, and for example, on the right, you see a prototypical example of a ribbon intersection or an arc intersection. We only want these kind of intersections. Okay, so a very simple fact is that every ribbon knot is sliced, and the way to see this is for a ribbon knot, we have a disk, and this disk is in the three-dimensional space in S3, and this disk intersects itself at arcs. So what we do is we have this extra 4-dimension when we move to slice knots. We have B4. So what we do is we have these two bands intersecting at the arc. We push one of these bands along this intersection into the 4 ball, getting rid of the intersection in the 4-dimensional space, meaning that we got a disk in B4 and this knot bounds this disk. So this shows that this is the basic argument showing that every ribbon knot is sliced. And the converse of this statement is the famous ribbon slice conjecture, which was conjectured by Fox. It says that every slice knot is ribbon. And this is a problem which is open, and there are some reasons for that. So it's a reasonable question to ask why it's hard to find a knot that's sliced but not ribbon. The first reason is obstructing ribbonness without obstructing sliceness is hard. The tools and invariants we use to show that a knot is not ribbon most of the time also prove that a knot is also not sliced. So it's hard to find differentiate these. And secondly, there are way too many knots. Like we have a good understanding of knots up to 12 crossing, but after that, like there are thousands of knots, and there's no reasonable way of approaching and trying to check every knot, whether it's sliced or not, a ribbon or not, and seeing if we can find a knot which is sliced but not ribbon. So having the basics of knots, the third class, like the family of knots or the construction of knots we want to have is called the 2-1 cable of a knot K. So let's move to the example. Okay, so first we take a knot K. Here I'm taking the figure 8 knot. We draw a parallel copy of our knot. Second, we look at the negative crossings and positive crossings, and the sum of these numbers, the algebraic sum of these numbers is called the right of the knot. For example, for the figure 8 knot, we have 2 negative crossings, 2 positive crossings, so the right is 0. And we are adding full twists as many as the negative of the right of this knot. For example, in this case, we are not adding any negative or positive full twists. And thirdly, if you look at the image on the left, you will see that when we just draw a parallel copy, it's not a knot, it's not an S1, it's 2 copies of S1. So to turn that into a knot, we have to introduce a positive half or negative half twist. We are adding a positive half twist by convention. And you can see the 2-1 cable of figure 8 knot on the right. Okay. And the idea is these knots will be able to tell us something about the slice-ribbon conjecture. So a theorem of Miyazaki and Kawachi tells us that the 2K1 cable, which is just a generalization of the definition I gave for 2-1 cables to 2K case, the 2K1 cable of a knot K is not ribbon if K satisfies the following properties. And it's important that we are obstructing ribbonness here and we are not mentioning sliceness in any way. So the first thing is that K is fibered. I will not be able to talk about what fibered is in this talk, but it's a property of knots. Some knots are fibered, some knots are not, but there's a bunch of knots which are fibered. Secondly, K is negative antichiral. This means that, for example, here, when you have the figure 8 knot, when you change, so you put an orientation on your knot, you change the orientation, and then you change all the crossings. And if the knot you get has the same orientation as is the same as the knot you started with, then we say that the knot is negative antichiral. And thirdly, we want the Alexander polynomial of our knot to be irreducible. Again, I will not be able to talk about what the Alexander polynomial is, but it's a polynomial we assign to every knot. It's a knot invariant, and it's very useful when you try to compute other knot invariants as well. And we want this polynomial for K to be irreducible. If these 3 properties are satisfied, then the 2-1 cable, and in particular the 2K1 cable, and in particular the 2-1 cable of our knot is not driven. So up to 12 crossings, less than 12 crossings, there are 8 knots satisfying these 3 properties. And if you look at the first knot, it's the figure 8 knot that we've been seeing since the talk began. And having these knots, it's again a reasonable question to ask whether the 2-1 cable of any of these 8 knots, which we have like some kind of an idea of their properties, we computed most of their invariants, is a 2-1 cable of any of these knots slice. And it's worth noting that any such example would be a counterexample to the slice-ribbon conjecture, because if they are sliced, we know by the theorem of Miyazaki and Kawachi that it's not ribbon, so that would give us a slice knot which is not ribbon. And the fact is that for the figure 8 knot, the 2-1 cable is not sliced. This was proved using so like some things we have to note about this theorem are that first, this was proved using Hager-Floer homology, which is not a particularly geometric method, and it's very complicated. I will not talk about this today. Secondly, the good news is there was an alternate proof, a much geometric proof using something called Kirby calculus, and the rest of the talk will be about proving this theorem using this new method. To do that, we have to talk about 4 manifolds first. So when we study 4 manifolds, we use these tools called Kirby diagrams. And again, I will not be able to talk about how we construct them, like why are these diagrams able to like help us study these 4 manifolds. But to give some examples, the one on the left is S2 cross S2. So we have the CP2, and then we have CP2 bar. The CP2 and CP2 bar are basically the only ones we will use in this talk. But to give a very quick recap of how these Kirby diagrams work, the idea is every form manifold can be constructed from a four ball, and you take a four ball, you attach these things called handles, 1 handles, 2 handles, 3 handles, and 4 handles. And the important thing is that 2 handles are attached along knots on the boundary of B4, which is S3, which is very similar to R3. So what we're doing is basically we're playing with these knots in S3, and there are some moves for them, which I'll talk about soon, and that way we can study four manifolds. Okay, so if X is a four manifold, then the first Kirby move is called the blow-up, which is basically just attaching a CP2 or CP2 bar to our knot, to our four manifold. So if our X is S2 cross S2, then what we're doing is we're adding, so we have the diagram of S2 cross S2 in the Kirby diagram, we just add the Kirby diagram of CP2 next to it, like they're not linked in any way. And then that translates to connect summing or attaching a CP2, or if you change +1 to -1 in the picture on the right, then that would be a CP2 bar. The second move is what we call the handle size. So like, for example, in this picture, we have a new CP2, but it's completely like, it's not connected to the diagram of S2 cross S2 in any way. So we want to like slide one of these knots over the other, and that's called a handle slide. And the way it works is it's not changing the four manifold, it's just changing the diagram. That's the important thing. And the effect of that, so for different knots, for different diagrams, the effect is different. But for CP2 and CP2 bar, for example, for CP2, let's say we have 3 strands of a knot from another diagram, and we have a CP2 around it, right? Like the +1, so that's called the framing, the +1 framed on knot around those 3 strands. If we slide that CP2 out of those 3 strands, the effect in the Kirby diagram is that we add -1, so a negative whole negative twist to those 3 strands. And again, the important thing is that we are not changing the four manifold. Okay, so having these basic tools from four manifolds, we want to use one of the some notions related to four manifolds, and that's the one that we're going to use today is called the minimum genus function of a four manifold. First, I need to recall some facts. So first of all, if you know what homology is, great. If you don't know what the second homology is in general, then you can think of the second homology group of a four manifold as the set of surfaces embedded in your four manifold, and there's an equivalence relation for these surfaces, and the equivalence relation is deformation. So if two surfaces are one can be deformed into the other, they represent the same homology class in the homology group. And for n copies of CP2 connect some m copies of CP2 bar, the second homology group is isomorphic to z to the n plus m. So this is the first fact we will need. And the second fact is, as I mentioned, every class in the second homology group of a nice four manifold can be represented by an embedded surface. So having these two facts, we can define the minimum genus function of a four manifold, which is this function which, so it maps, it goes from the second homology group of R four manifold to Z. It takes a second homology, class, looks at all surfaces representing the second homology class, like the nice surfaces, they had to copy and stuff, but it looks at all surfaces representing this homology class and finds the minimum genus of a surface representing this homology class, and that genus is the value of this function. And this is a big problem. Like, it turns out that the minimum genus function tells us a lot about the four manifold that we're working with. One of the very famous conjectures about this was the Thom conjecture, which was settled by Cronheimer and Rofka in 1994. And it basically is that the minimum genus function of CP2 is given as follows. So CP2, as I said here, the second homology group of CP2 is just Z. So this is a map from Z to Z. And if you take a second homology class A, then it turns out the minimum genus function of CP2 is 1/2 times A minus 1 times A minus 2. And it turns out this is a specific instance of it under theorem. It's called the symplectic Thom conjecture, which was proved by Ojot and Szabo in 1998. It tells us that if you know symplectic geometry, this will make sense. If not, like it doesn't matter. A symplectic surface in a symplectic form manifold is genus minimizing in its homology class. So if you have a symplectic manifold, then to determine the minimum genus function of that manifold, you have to construct a symplectic surface representing that homology class, and then you will have the minimum genus function. Okay. And it turns out, since like this is a very useful tool, of course, computing the minimum genus function of other form manifolds is a very ambitious task. But two results that we will use today are the following. The first one is that for 2CP2, the class 1,3 cannot be realized by a sphere. And secondly, this was proved by Brian. The first one was proved by Curver. The class 2,6, again, in 2CP2 can be realized by a surface of genus at least 10. So for example, this class cannot be realized by a surface of genus 9. Okay. Before moving on to the main proof, we will need this very useful trick. So what we do is we take two strands which are consistently oriented. We make this smart move. So we create 3 strands out of 2, and then we blow up with a CP2. So when we do that, as we talked about handle slide before, when we, so we have this blow up, we handle slide that out. When we do that, we introduce -1 hole twists to these 3 strands. And when you isotope, meaning like when you deform these 2 strands, it turns out that at the end you get 2 whole negative twists. So we started with like no twists, we blew up, we isotoped, and we got 2 whole negative twists. And if you change the orientation of the second strand, then what happens is when you look at the blowing up pictures, like the second picture here, the first one, the algebraic intersection number of the strands with CP2 is 3, and for the second one, it's 1. And we will come back to this. This will be useful. Okay. So the last part, finally, the proof of the main theorem. First of all, we want to prove a fact that's known by like everyone in knot theory, the fact that the figure 8 knot of the figure 8 knot is not sliced. There are different ways of proving this, like there are invariant proving this, but we want to do it in a specific way that will help us with proving that the 2-1 cable is not sliced. Okay, so step 1, we take our knot, the figure 8 knot, and we turn it into the unknot by blowing up twice. So you can see the figure 8 knot on the left, and when I highlight with the yellow, I will do a blow up move there. So when I blow up, I introduce a -1 twist, so I'm getting that knot. But now I can isotope it into this. So you can see that the second picture and the third picture are basically the same thing. I just deformed them. And I blow up again to the yellow part, and I change the crossings. And at the end, the fourth thing is obviously an unknot. So we unknotted the figure 8 knot by blowing up twice. Okay, that's nice. What does this give us? So first of all, we blew up twice. So we are in something related to 2CP2, right? We blew up twice, we added 2 CP2s. But if you think of, so we have S3s, and if you think of these as like moves, what we're doing is we have an S1. So we have an S1, which is a figure 8 knot in S3 on the left, and then we turn that into the unknot in S3. So we have an S1 cross an interval embedded in 2CP2, but on the left, we have the S3. So this is like a cylinder, and we have the boundary, and as we have to cap that off to get to 2CP2. So we are missing 2B4s. So basically what we got is we have an S1 cross interval embedded in 2CP2 minus 2B4s. Okay, so if the figure 8 knot were sliced, so we are going for a contradiction here. If the figure 8 knot were sliced, we could cap off this 2CP2X, which is 2CP2 minus 2B4s, with 2B4s with disks embedded in them, because being sliced means there's in B4, there's a disk bounding this knot, right? So we could cap off at the end, that would give us a sphere, because there's no genus here, there's a sphere in 2CP2. But if you look at the homology class represented by the sphere, then we look at where we blew up. And if you remember, when like I had this trick, and we're using this trick on the left, since they are not consistently oriented, the corresponding algebraic intersection number is 1. And for the second one, it's 3. And that algebraic intersection number gives us the homology class of the sphere in the second homology group of 2CP2. So this sphere that we constructed represents the homology class 1,3 in 2CP2. But that's a problem, because if you remember that Kerver said that the class 1,3 cannot be represented by an embedded sphere in 2CP2, and this is a contradiction, and it means that the figure 8 knot cannot be sliced. And the question is whether we can use this method to prove that the 2-1 cable of the figure 8 knot is not sliced, and the fact is yes. How do we prove that? We do the same thing. So what we do is, like, when you have the 2-1 cable, it looks a lot like the knot you just started with. And it turns out if we blow up at the same places we blew up before, if we do all the isotopies the same way, the knot we get at the end, because we're introducing a bunch of negative twists here, the knot we get at the end is not the unknot, but the torus knot, the 2-19 torus knot, which has slice genus 9. And again, using the same argument, if the 2-1 cable of figure 8 knot were sliced, then we could cap off from the left. So again, we are in 2CP2 minus 2B4s. We could cap off from left with a disk, because it's sliced, and from the right with a surface of genus 9. But Brian told us that this class. So what's the homology class of this genus 9 surface? It's 2,6. Why? Because in the first case, in the lemma for the figure 8 knot, we had 1,3 and we doubled everything. So the homology class is 2,6. But this is a contradiction, because Brian told us that the class 2,6 can be realized by a surface of genus at least 10. So the 2-1 cable of the figure 8 knot is not sliced. And this is the geometry proof of the theorem that I mentioned earlier. And that was my goal today. So thank you.